All right. So now I can finally state the theorem that we wanted to or prove the theorem that I want. So this is the characterization of cuspidal inertia groups inertia as cyclotomes. And this is over for number fields. Okay, so let's let x over k be a curve over a number field. A number field. Okay, we'll let I be a subgroup of the geometric fundamental group of X. This is pi 1. And I'm going to, let's do xk bar with some point here. Okay, so this is the geometric fundamental group. Then we have the following statement that I is a cyclotome if and only if there exists some x which is a cusp of x. Okay, so again I'm using the notation that this is the complement and the compactification. Such that, I guess, and there exists some x tilde in x tilde, this lifting x such that I is equal to the inertia group over x with respect to that lifted point. Here's the proof. Okay, so the this direction's easy. So if x is a cusp, I x tilde over x is a cyclotome for the absolute Galois group of this number field by the tame inertia character, or just the inertia character in this case. Okay, so this is the tricky part, and this is what we're going to do. So suppose that Z is a cyclotome. Okay, and let's suppose it's so. And suppose that Z is not a cuspidal inertia group. Is not a cuspidal inertia group. Okay, so this implies by a certain characterization. So this is this lemma that we had of cuspidal inertia groups, that there exists some L which is prime. There exists an H which is open. And there exists some W in H intersect Z such that, okay, W is not in this group generated by the Frattini subgroup for L. Oh, sorry. H to the L infinity. And then this thing generated by all conjugates of inertia. So let's call this script I intersect H. Okay. And so this is group generated by all conjugates of all inertias. So inertia groups of cusps. Okay, so now we're going to work with this H to derive a contradiction. Okay, so let's let H tilde be the normalization, so the normalizer of H and pi of x, and we'll let K tilde be the group, the field corresponding to the image in GK. Let's call this capital K tilde. Okay, so also we'll let let's fix some other notation. Y to x be the cover corresponding, and I did it again, to H tilde. So in other words, H tilde is pi of y. So this is this open subgroup. Okay, so so from the theory of weights, well, weights. Okay, I'm going to say something else that's going to have to do with the theory of weights. We have an exact sequence of GK tilde modules. Okay, and it's like so. So actually, let me just write it like this. So we have an exact sequence of G of K tilde modules, like so. And this just follows from the inertia sequence. Okay, so this is a global thing. So here is the cusps. This is the free group generated on the cusps. Okay, let's just continue this here. So this one goes down to here. To okay, this is equal to okay, and to and this is again, so this is okay, so we have this following exact sequence. Okay, and this just follows from okay, so this follows from the description of this kind of what do I want to say? I want to say this follows from the inclusion of the fundamental group of y into y bar. The kernel of that is the thing generated by inertia. But since inertia has a single generator, that's what this is coming from. Okay? Now I'm going to state the part that has to do with weights. Okay? So let me give some names to these. First, let's call this G0, and we'll call this map G. Okay? Okay, so this sequence is really related to the weight filtration. Okay, so here, okay, so more precisely, if we restrict to a local field, then and tensor up to QL, we get the following. So if we okay, so I need some notation. So so we're gonna let VL of y be TL of y, tensor QL. We're gonna let same thing for VL y bar. And then okay, and then we're gonna take IL to be the image, or let's say the co-kernel of G0. So this is just really the thing generated by inertia. And then JL will be IL tensored up to QL. Alright. Okay, so we have these. Then what this is saying is that this sequence, okay, so if we let these, the sequence, then the sequence here, 0 to JL to VL to V, so VLY to VLY bar is really the weight filtration. Let's say the weight filtration sequence. And what do we mean by this? So we mean that VL y minus 2 is equal to JL. So we mean that this means that the okay, so if we look at the -1 graded piece of VLY, so this is going to be VL minus 1 VLY minus 2, and this is just going to be isomorphic to VLY bar. Okay, so this is the -2 piece. So this is pure of weight -1. Okay, so to make sense of weights, this is why we needed to restrict to the local field. Okay, similarly, we also have that this part here. This is just going to be VL y minus 2, VLY minus 3. This is 0, so this is just VLY minus 2. Okay? Okay, so we have all these things. Alright, so this is what this is saying. This is, now, essentially what we're going to do is we're going to see that, so using that, this guy is a cyclotome. Implies that if we look at this representation here, this is W. Okay, so now we can, so this could be for G in GK tilde. Okay, this is going to be the, okay, and W bar, I guess, is going to be the image in, so W bar is the image in here. So here we need to take the abelianization and then the pro-L quotient, okay? But if we do this, we find that, okay, we do this, we find that this guy here in the quotient is isomorphic to ZL minus ZL1, okay? Okay. So as GKV tilde modules, as let's say a GKV tilde module, it has weight minus 2. All right. So it has weight minus 2. So this implies that that W bar must be in the weight 2 piece, IL, which is by definition, well, JL intersect the integral part, TLY. Okay, but this is a contradiction. Okay, why is this a contradiction? So it turns out that that this condition here, where is it? This condition here, using what I just described here, so this sequence. Okay, so let's call this something. Okay, so let me just say this, is that condition star here is exactly the characterization of the weight 2 space. The integral, integral, how do I spell that? Weight minus 2 subspace of VLY. Okay? And that's how you conclude the proof. All right, so I think that's all I wanted to say. So this is the local version of, the global version of showing why every cyclotome, every cyclotome is actually a cuspidal inertia group. Thanks for watching.